Okay. All right, so let's start by going over this problem. Now, the first thing we want to take a look at is we want to take a look at the instructions before we jump right into the question. So it says that we have an unbalanced reaction between potassium permanganate and acidified iron 2 sulfate in a redox reaction. Now, you guys probably haven't seen that term in a long time, right? I think we went over redox in like end of September or early October. And so what we're going to be doing is we're going to be taking a look at this reaction right here. And the first thing we want to do is write the half reactions that occur below. Now, I guess, what's that thing called? Where you have letters that stand for stuff? Thank you. What was that? Yeah, oil rig. Yeah, you want to take a look at, you want to memorize this term right here, oil rig for oxidation reaction. Now, oil rig, okay, this can bother me all day. What's this called? When you have letters that stand for certain words? Acronym. Thank you. Acronym. That's why I don't speak English. Okay, so we have oil rig as the acronym for oxidation reaction. So oil rig stands for oxidation is loss. So it's when you lose electrons. And reduction is gain, right? When you gain electrons. So when we take a look at this equation right here, we want to figure out which one lost electrons and which one gained electrons. That's going to tell us the oxidation reduction. So all we need to do is follow the elements. So let's start with the ions because they're easier. So if we take a look at iron, right? Iron started off +2 and then became +3. So did it gain or did it lose electrons? Yeah, it lost electrons, okay? Which means that this is oxidation, right? So your oxidation reaction is going to be, you're going to start with Fe2 plus, it's aqueous. And then what did it turn into? It turned into Fe3 plus aqueous. But for half reactions, you want to mention how many electrons you lost. So basically, this reaction is telling us that Fe2 plus lost an electron. So on the product side, again, we need to balance it. So we're balancing the charge. You got this. Okay. Now, if you guys haven't memorized oil rig yet, I do recommend that you do because a lot of questions on the AP test do have to do with oxidation reduction. They like to kind of combine it with random topics. And so just make sure you guys memorize the acronym. All right, now we're going to take a look at the reduction reaction. So we're going to be taking a look at which one gained electrons, okay? So let's take a look at the ions again. So here we need to look into the actual molecules in order to figure out which one got reduced. So if we look at H plus, right? The oxidation number for H plus is +1, right? For an ion, it's just the charge. However, if we take a look at what hydrogen went into H2O. Now, the easiest way to look at oxidation numbers is to memorize that O is always -2, okay? O has an oxidation number of -2. So hydrogen here has to be what? Yeah, +2, but there's 2 of them, so it'd be +1, right? So +1, but I'll just put a ×2 underneath to show that it was that. So what happened to hydrogen? Did hydrogen gain or lose any electrons? No, it kept the same oxidation number. So we can just erase that. We don't really need. Yes.
Redox?
Yes, sir.
Big boy redox?
Big boy redox. FRQ redox. Okay, so we don't need to worry too much about the hydrogens. Okay, let's move on to the next element. We have manganese. So I want you guys to take a second, if you guys haven't, I want you guys to calculate the oxidation number for manganate here.
Is that manganate or permanganate?
It's manganate because it's permanganate, sorry. But I meant just manganese. Yeah. Because we're trying to see if it was.
Manganate must be MnO3.
Yes. Is it still -1?
Yeah.
It is -1. All right, guys. So if we have MnO4, let's figure out the oxidation numbers. So we know that at the very end, since it's -1, it needs to end up with an oxidation number of -1, okay? So we don't know manganese, but oxygen is easy, right? Because it's usually going to be -2. So if we have 4 of them, we have -8. So what does manganese's oxidation number have to be? Yeah, it's gonna have to be 7, +7. So manganese started with +7, and then what did it turn into on the product side? +2. So that shows us that it gained or lost. It gained electrons, right? Because it was super duper positive, super duper happy, and then it just became a little bit happy, +2. Okay, so that means our reduction half reaction right here is gonna be with manganese. So we have manganate. So we're gonna start off by writing manganate. And then we have manganese right here, right? However, we need to make sure that it's balanced in the half reaction. So since we talked about oxygen right here, we need to include the oxygen. So we know that it's talking about H2O still. And since there's hydrogen here, we need to add hydrogen to the reactant side. Okay, so again, we need to make sure that all of our equations are balanced, and that includes in the half reaction. So we have H plus as our other reactant. Now, since this is a reduction reaction, are we going to have electrons on the reactant side or the product side? Remember, it gained electrons. Who thinks it's going to be on the reactant side? Okay, who thinks it's going to be on the product side? And the rest of you guys are just looking at me. Okay, it's going to be on the reaction side. And it's because, again, the electrons need to bond with manganese, and that's how it can gain electrons, right? It has to be on the reactant side.
I'm so glad I'm here.
Are
I'm
you?
gonna lie to you. I haven't done it for 6 years.
Really?
And I'm gonna do it next week.
Oh, for sure. Well,
And you just graduated from college 2 years ago, so you just finished doing this.
2 years ago, I'm not that young, Pepe. I'm not that young. I know I look like I'm 14, but I'm actually 16. I'm actually 16. I act like I'm 12 though. Okay, so we have the electrons. So now we just need to balance this equation. Okay, so how many electrons did manganese gain? 5. So we can just put a 5 in front of the electron. So 5 electrons. Okay, and so now we just need to balance. We have 4 oxygens on this side. And so we need to make sure we have 4 oxygens on this side. So we put a 4 in front of H2O. And now we have 8 hydrogen. So we need to put an 8 right there. And so there you go. That's going to be your reduction half reaction. Oh, and I forgot to put aqueous here. Sorry about that. Okay. So I know that was extremely complicated. And it's been a long time since we looked at oxidation reduction. So just make sure that you guys are aware of the half reactions, and just that to make sure that they're all balanced out. Yes, Mr. Pepik.
Are they gonna want us to add those together?
We will for part B.
Got it.
Yeah.
Sorry.
No, you're
Like-
good.
Tell me they don't. Maybe we don't have to do that anymore.
They are. Yeah. And bouncing off Mr. Pepik's comments, we're gonna go into the part B where it says, what is the balanced net ionic equation? Now, if you guys remember, the net ionic equation has to do with the ions, right? We need to combine everything. Sorry, do you have a question? Oh, my bad. It looked like your hand was up. Sorry, my eyes are playing tricks on me. Okay, so we need to combine. We need to combine these equations, and we're gonna write the balanced net ionic equation where we take into account every single one of the ions inside of the equation. Now, lucky for us, we have all of the ions here. It's already broken apart for us. So all we need to do is copy down this equation right here that is given to us. So take a second to copy that down for part B. And then we just need to balance it, because the net ionic equation is just going to be the equation with the ions. Now, if you guys notice, this has to do with potassium permanganate and iron 2 sulfate. So in this problem, they've already broken it down into the ions for us because potassium permanganate is KMnO4 and iron 2 sulfate is going to be FeSO4. But we don't have we don't have K and we don't have SO4 because there's no net change in the reaction. And so they've already broken it down into the net ionic equation for us. Okay, so all you guys need to do is balance this equation right here. Okay, so take a second to copy it down. I'll give you guys about a minute if you guys want to try balancing it, but I'm going to give you the answer just so we can move on to the next part.
I've never done it that way. That is a great idea. Just copy it down and then just fill in the number of electrons and everything else, right? That's a really good idea.
Thank you, Mr.
I was
Pepke.
always taught, boom, now you got to go through and add everything up. It was already done for us. So I'm glad I'm here. Don't get people like this all the time.
People like you.
I was an art major. Chemistry.
I don't know chemistry either. I'm just making this up as I go along.
That's a good way to go.
Yeah, just figuring it out. Okay, so take a second to balance it out, and then that'll give us the balanced net ionic equation. Mr. Pepke, stop cheating. Stop cheating, Mr. Pepke. You can't look at our answers.
Copies of the,
For today, yeah. Usually I have it posted on Canvas, but I wanted them to have a physical copy. Yeah, what's up? Great. Manganese was +7 because, so if you take a look at the oxidation numbers right here, the charge is -1, right? And so that means when you combine the oxidation numbers of manganese and all the oxygens in there, they have to equal -1. Oxygen is 99% of the time going to be -2. So if there's 4 of them, that makes them -8, right? And so to bring it down to -1, manganese has to be 7 in order to bring it down to -1 because it needs to balance out the -8 from the oxygens. Make sense? Sure. All righty, guys. So I'll just balance this real quick for you guys. But if you guys want to balance it, you're going to have 8 hydrogens or H plus. You're going to have 5 iron 2 ions. And then you're going to have a 5 in front of the iron 3 ions. And you're going to have a 4 in front of the H2O. And that's how you would balance it out. Okay. And for the net ionic equation, you don't need to add the electrons. That's only for oxidation, reduction, half reactions. Okay. Did I do that correct? I did. So the answer to part B is this right here. It's just going to be this balanced reaction. Okay, any questions? Yeah. Good question. Why does Fe have a 5? Oh, for the electrons. Yeah, for the electrons. Yeah, you don't write the electrons in there, but because we did have 5 electrons, we need to have the 5 for the Fe. Yeah, because if you combine these two reactions, you see how there's 5 electrons on the reactant side for the reduction. You're going to need 5 for the product side as well. Okay. Good question. My bad, I forgot to mention it. Isn't this fun, guys? Putting everything together. If I was you, I'll do the middle finger one. All right, let's move on to part C. Everyone got this written down somewhere? Okay. All right. Before we move on to part C, we want to take a look at, excuse me, this table, or before we read the table, let's read the instructions. So it tells us that the solution, is 0.150 molarity potassium permanganate is placed in a burette before being titrated into a flask containing 15 milliliters of iron 2 sulfate. Now, I'm going to draw a picture real quick just so you guys can visualize, but you guys remember when we did the titrations, right? We have that that long burette and it goes into the flask. Now, what this is telling us is that we have potassium permanganate in the burette, so KMnO4, and then we're dropping it into FeSO4. Okay, and then the concentration is 0.15, and then there's 50 mils of iron 2 sulfate on the bottom. Okay. Now, what it's telling us is the colors of the solution. So if you have a H plus solution, it's colorless. If it's Fe2 plus, it's pale green, etc., etc. Okay. So far, so good. All right. Now, what this problem is asking in part C is it wants us to describe the color of the solution before titration, during titration, and at the end of titration. And so what we need to do is we need to figure out what ions are present, because that's what's going to tell us the colors, right? Because depending on what ion is present inside of the solution, that's going to tell us what color the solution is going to be. So you're going to need the reaction with you. And so just make sure you have the reaction somewhere written down. And so let's figure out what ions are present before the titration. Okay. Okay, so it's telling us at the very beginning, before titration, we're focused on the flask, okay, the flask at the bottom. Okay, now it's telling us that the flask is a solution of FeSO4. Now this is an ionic compound. So what are the ions that are present inside of this solution? No, there's some ions. FeSO4 is ionic, so it breaks down into its ions. So what ions does FeSO4 break down into? Yeah, Fe, yeah, 2 plus, and then, yeah, SO4 2 minus. Good. Now, there is one other ion in there that's on this chart. Anyone want to take a shot at what it is? Yeah, hydrogen, because there's water, right? And we met, like, it's in your textbook for like one sentence, but water auto ionizes, which means it releases some of the ions automatically. So water is going to release H plus. Technically, there's some OH minus in there as well, but it's not on the chart, so we don't really need to worry about that. So before we start titrating, there's going to be some Fe2 plus, SO4 2 minus, and H plus. Now, based on that information, we can figure out what color this solution is. Now, H plus is colorless, so it's not going to contribute. Okay, so we don't care about H plus. It says that Fe2 plus is pale green, and then we got SO4 2 minus, which is colorless. So if two of them are colorless and one of them is pale green, what's the color of the solution? Yeah, pale green. So the answer to C1 is going to be before titration, the solution is going to be pale green. Okay. Hopefully that makes sense. All right, should we move on to the next part? Okay, so now we're gonna look at the color during titration. Okay, so now what we're gonna be doing is we're gonna be dropping some of the potassium permanganate. Now we know that potassium permanganate is K plus, or ionizes to K plus and MnO4 minus. Now, one key thing that you might fall, like the trick that you guys might fall into it is to say that, hey, there's MnO4 minus, it must be dark purple, right? However, it's important for us to remember that we're looking at the color inside of the flask, okay? So what would we see in the flask? Now, when you put KMnO4 into this flask, the reaction is gonna start, right? And so what happens is we're gonna start seeing some of these products being formed, okay? And so during titration before the endpoint, we're going to start to see KMnO4 reacting with FeSO4. And so what we need to do is we need to figure out what products are being formed during the reaction. Now, before titration, we said that we were pale green. Okay. And as KMNO4 reacts with the Fe2 plus, it's going to start changing color. And so that's what we're trying to figure out. What color is it changing into? Okay. So if you guys take a look at the reaction that we did for the net ionic reaction, okay, what does MnO4 minus turn into when it starts reacting with FeSO4? Yeah, MnO4 minus, when it goes into this flask, is going to start turning into Mn2 plus, right? Because it's going to start reacting with the stuff in there. Okay, and then what does Fe2 plus turn into? What's on the product side? Yeah, Fe3 plus. So we're going to start losing Fe2 plus and start gaining Fe3 plus. And we're going to start losing MnO4 minus and start getting Mn2 plus. Okay, now in the net ionic reaction, we know that SO42 minus doesn't really matter, and it's colorless anyway, so we can just kind of forget about that. And H plus is also colorless. Okay, so if we take a look at the new products that are being formed, we said that Mn2 plus is being formed, and we said that Fe2 plus is going to turn into Fe3 plus. Okay, so this is where it's going. So if you guys take a look at the flask, we said that it was pale green. We added some of this dark purple stuff, but the dark purple stuff turns what? Colorless, right? And so the only colors we're really caring about is what happens with Fe. So during titration, what color do we start seeing the pale green transition into? Yellow. So during titration, before the endpoint, what we're going to see is a solution that becomes less green and more yellow. Okay. So it's going to go from pale green and it's going to start turning a bit more yellow. Okay, so that's the answer for C2. Okay. All right, now at the end of titration, what's going to happen is we are going to, excuse me, we're going to lose all of the Fe2 plus. So the only thing left in there is Fe3 plus, which we said is yellow. Okay. And then once the Fe2 plus is all reacted with, what's going to happen is we're going to end up with some MnO4 in there as well. Okay, which we said is going to be dark purple. So at the end point, we're going to have some combination of yellow and dark purple. Okay. And that's because all of the Fe is going to react and it's going to turn to Fe3 plus, and then we're going to have some leftover MnO4 minus left in the solution. So at the end, you're going to have some mixture of MnO4 minus in there and Fe3 plus, which is what we see in the reaction. Okay. Kind of confusing, right? A lot of visualizing, but at the same time synthesizing that with chem concepts can get kind of tricky. Okay. Yeah, what's up? So yeah, you would see a little bit. Remember when we titrated, it was like clear and it starts turning pink, right? In the titration that we did, but you saw how like there were wisps of pink and it disappeared. It'd be the same thing. You would see like wisps of dark purple, but then as it reacts with the rest of the solution, it would start turning more yellow as it reacts. Yeah. So yeah, as long as you're able to, the important thing is to figure out what ions are present. So if you can list the ions that are present and then justify that with the color, justify the colors with the ions present, that's totally fine. Yeah. Good question. Any other questions about part C? All right. Yeah, what's up, Ray? The second one, the ions that are present is we're going to have Fe2 plus transitioning into Fe3 plus, and then we're gonna have MnO4 minus excuse me, transitioning into Mn2 plus. And so since Fe3 plus is yellow, you're gonna start seeing some yellow, and then you're gonna start seeing the Fe2 plus get less green. And this is gonna be colorless, so we don't care about the Mn2 plus. It's right here. This is part 2. Alrighty, let's move on to part D. And I think you guys will like part D a little bit more because this is just going to be some dimensional analysis, some of that math stuff that's pretty simple. So if we go down to part D, you'll see that if 15.55 milliliters of permanganate are added to reach the endpoint, what is the initial concentration of the iron 2 sulfate? Okay, now we'll block part 2 for now because we're looking at part 1. So what this tells us is the volume of permanganate is 15.55 milliliters, okay, KMnO4. Okay, and it's asking us to find the initial concentration of iron 2 sulfate. So that's what we're looking for. We're looking for the molarity of iron 2 sulfate. Okay, now we have the volume, but we also have the concentration of permanganate, right? What's the concentration that was given to us? If you look at part C. Yeah. So if you guys didn't catch that, if you go up here, you'll see that it's 0.15 molarity. That's the concentration. So the concentration is 0.15 molarity KMnO4. Okay, now we know that the molarity formula is moles over liters. So here we're going to be looking for the moles because then we can do a conversion using the balanced equation, right? So we can calculate this by doing moles is equal to molarity times volume. And so all we need to do is plug it into our calculator. 15. Oh, we got to convert this into liters first. So we would have 0.01555 liters times 0.15 molarity. I'll pull out my calculator. Okay, so we have 0.01555 times 0.15, and that'll give us that many moles. So 0.00233 moles of KMnO4. Okay, now we don't really care about the potassium because in our net ionic equation, it doesn't really play a difference in the reaction. So we don't care about KMnO4, but we know that there's 1 mole of MnO4 within KMnO4, so we can just eliminate the K. Now, what we're trying to do is we're trying to find the initial concentration of iron 2 sulfate. Okay, so what we're going to do is we're going to set up a mole ratio where we're going to use our balanced equation to cancel out the moles of MnO4 minus, and we're going to try to find Fe, what it reacted with, so Fe2 plus, okay? Because again, SO4 is not that important because it doesn't do anything in the net ionic equation. So we're going to be looking for moles of Fe2 plus, okay? So if you guys take a look at your balanced equation, what's the number in front of Fe2 plus in our balanced net ionic equation? Yeah, 5. And what's the number in front of MnO4 minus? Yeah, 1. Good. Good job, Mel. So what we're going to do is we're going to take these two values and then multiply it. And that is going to give us the concentration of that's going to give us the moles of Fe2 plus, excuse me. So this number times 5, and that'll give us 0.0117 moles of Fe2 plus. Okay, so just to reiterate, we started with the volume and concentration of KMnO4. We turned it into moles. We said that we don't care about K because it's not part of the net ionic equation. And then we just converted it into the ion that we wanted. Because this is a 1-to-1 mole ratio, if it's going to have the same number of moles, the number of moles of Fe2 plus is equal to the number of moles of FeSO4. Okay. That's why we're not looking at the ions, the spectator ions, the ones that don't do anything. All right, almost done. Okay, all we need to do now is we need to find the molarity, and we know that molarity is equal to moles divided by volume, right? What's the volume of our iron solution? You take a look back at part C. Yeah, and so we just need to convert that into liters, so it's going to be 0.05 liters. And again, if you don't know where we got that volume, it's right here, 50 milliliters. And so this is going to be the equation that tells us our final answer. So all we got to do is take that value and then divide it by 0.05. And there you go. That is the concentration of your iron to sulfate solution, 0.233 molar. Am I overwhelming you guys? No, hopefully not too much. Okay. I do want to mention to you guys as we move on to second semester that this solution stuff is going to be very important. I think about, don't quote me on the number, but like 60-70% of the AP test is based on the stuff we're going to cover second semester. So equilibrium and acid-base equilibrium. And equilibrium is usually about concentrations in solution, so this molarity stuff. So just make sure that you're very comfortable using this equation because that's what the majority of the test is going to be. I think our longest unit this year is going to be like a month and a half, and that's all equilibrium, so all molarity stuff. So you got to be able to convert between these things very comfortably, okay? Okay, so that's D part 1. Now let's go to D part 2. And so it tells us the actual concentration of FeSO4 is 0.25 molarity, and you need to calculate the percent error. Now, this is pretty simple. We have our concentration that we calculated, which is 0.233. And so what we need to do is we need to calculate what the error is. Okay, so I'm going to write that down. So 0.233 molarity FeSO4. That's our calculated one, right? Okay, but the actual is going to be 0.25 molarity. So calculator or experimental. Okay, so if you want to find percent error, this is the equation that you guys can use. I know some of you guys can kind of figure this out with your math skills, but basically what you're going to be doing is you're going to be taking the actual minus the experimental and then just divide it by the actual because that's your 100%. Okay, and then times it by 100. And that's going to give you your percent error. So the equation is going to be actual minus experimental divided by the actual. Okay, so take a second to calculate that out. Oh, that one you don't need. That one, just leave it on the side. I'll take care of it. Appreciate that. Alrighty, guys. So if we punch this into our calculator, we can just do this: 0.25 minus 0.233 divided by 0.25. So we were off about, and times 100. So we were off by about 6.8%. Okay, so 6.8% error, which is actually pretty good. All right, any questions about that part? And then we'll move on to the last portion, and then we'll take a break before moving on to the second FRQ. All right, so if there's no other questions, let's move on to the next portion. So we're gonna move on to part E. So in E, it's asking us, they give us two errors that could have happened during the reaction, okay? And it's asking if those two errors could cause the deviation that we saw in our calculation, right? Because we calculated 0.233, but we said the actual, is 0.25. It's asking, can option 1 and option 2 cause those errors? So let's take a look at option 1. Okay, it's asking us if 55 milliliters of FeSO4 was added to the flask prior to the titration instead of 50 milliliters. So if we had more volume of FeSO4, could it have led to our error? Okay, so what we need to do is we need to calculate this difference because it's asking us to justify your answer quantitatively. Quantitative means with numbers. Okay, so what we saw earlier in the problem is that if we had 50 milliliters of FeSO4, right? How many moles of FeSO4 was that? 5 is the ratio. You guys remember what the number of moles were in your calculations? That's going to be for your MnO4. Yeah, so just make sure that you guys label all your numbers because a lot of times you will have to refer back to it. So if we really had 50 milliliters of FeSO4, this is how many moles of FeSO4 we would have. However, if we had 55 milliliters of FeSO4, okay, we can calculate how many moles we had of that. So take your calculator, see if you guys can figure out how many moles of FeSO4 you would have if you had 55 milliliters. So if we had 55 as our volume, we could look at it two ways. We can test it based on the 0.234, the experimental one, or the actual one. Okay, that we could have found two different moles. So if we compare those two values, we would see that you need to multiply the molarity by the volume. So 0.234 times 0.055. And so what we could have had was we could have had 0.012 129 moles if we tested it with the experimental value. And if we did it with the actual value, we could have gone 0.25 times 0.055. Okay. So the question is asking us, could our deviation, right? Because this is the actual, but then experimentally, this is what we found, 0.234. Could this have happened if the volume was bigger? Okay. So if you guys take a look at it, what happens to the number of moles as we go, if we do it like this, if the volume is bigger, so if the volume is larger, what happens to the molarity? Yeah, it's gonna increase, right? Because the values are gonna get bigger, right? We have 0.0117, 0.0129, and then this one. So regardless of how you look at it, the molarity is gonna go higher. So if you take a look at the problem earlier, the actual was 0.25. Was the actual larger or smaller than what we calculated? Because we calculated 0.234 molarity. Are you guys just tired now? It's just too much. Yeah, it's gonna be, the molarity is larger, right? So what that means is, okay, we can start writing our answer now. So you can say our actual, or the actual molarity of the FeSO4 solution is larger than the experimental. Okay. Okay, but then we see based on our calculations, the larger the volume of the solution, the higher the molarity, right? Because we see this right here. So that's going to be what we have so far. So now you just want to wrap it up because you talked about what you got in your experimental and your actual, and then you see what theoretically it should be. Okay, and so the actual molarity of the Fe2 solution is larger than the experimental value, larger the volume. And then so what we can do is now we can talk about the volume. So you can say that 55, using a 55 milliliter solution will increase the molarity. Therefore, this error can explain our deviation. Okay. Okay, so all we need to do is basically compare the numbers that we had, and then just based on the patterns that we see, just and then just conclude it, just wrap it up together. And then you guys can do the same thing with number 2. Try that out. Okay, but we're gonna take a quick break. Any questions? All right, so I'm gonna pause the recording for a bit and I'll give you guys a 7-minute break. We'll come back and then we will do the second FRQ together, okay? Before we move on to the next one, I do wanna mention, Mel pointed this out, but I did make a mistake, and looking at it now, I feel really stupid because it makes no logical sense, the answer that I wrote. But if you have a larger volume, the molarity has to be smaller, not bigger. And so I highlighted the keywords that I messed up on. The larger the volume, the lower the molarity. I wrote larger or greater, which makes no sense at all because if you increase the volume, it should make it lower molarity. And so the 55 milliliter solution will decrease the molarity, and so the error cannot explain. Sorry, guys. So part one, it does not explain the deviation because it's gonna lower the molarity. So that was my fault. Thank you, Mel, for pointing that out. You should be teaching the class instead of me. Okay, so again, sorry about that. And let's move on to the next one. The next one is significantly easier than this previous one because no math, actually a little bit of math, but we also just learned this. So hopefully it's a bit more fresh in your minds. So we have two different electron dot diagram representations for an acetyl ion, which is C2H3O-. And so what you want to do first is for part A, we're going to use formal charge to determine which is the more likely structure, okay? So we learned about formal charge, but if you guys don't remember the formula for formal charge, okay, but formal charge is going to be the number of valence electrons minus the number of bonds minus the number of lone pairs, okay? And if you like the other way, it's easier, okay? Minus sticks minus dots. So formal charge is valence electrons minus bonds minus lone pairs, or minus sticks minus dots. And so what we're going to be looking at, we're going to be calculating the formal charge of the carbons and the oxygens inside that structure, because hydrogens are always going to have just one bond. It's going to be 0. So you're going to calculate the formal charge here for carbon, carbon, oxygen, carbon, carbon, oxygen, and then see which one makes the most sense. Okay, so I'll give you guys about 2 minutes to do that. At least try to get the left one done, and I can give you guys the ones for the right. Okay, take a second to try that out. All right, guys, let's start going over it. If you're finishing up, feel free to finish up. But if you know how to do formal charge for one of them, you should be good with the other ones too. So if we take a look at the structure on the left, let's do formal charge for that carbon. So carbon has 4 valence electrons. It has 1, 2, 3, 4 sticks, 4 bonds, and so it's going to be minus 4. And then no lone pairs. So this carbon is going to have a formal charge of 0. Okay, hopefully you guys got that. Same thing with this carbon, 4 valence electrons, minus 1, 2, 3, 4 sticks, minus 0 dots. So it's going to have a formal charge of 0. oxygen is going to have 6 valence electrons. You're going to subtract 1 bond, 1 stick, and then 6 valence electrons. So this one is going to have the formal charge of -1. Okay. So I'll erase all the math, but okay. And then I'll just give you the formal charge for these ones, just because we are running out of time. You should get a formal charge of 0, -1, and 0. Everyone got that? Okay. So based on the formal charge rule or formal charge rules that we know that we want everybody to be 0, but here we can't do that. But we want the most electronegative one to have the negative value. So which one of these is the correct structure? Yeah, the one on the left, because this is the one that has oxygen with the negative formal charge. Okay, so this is the guy that we like, and this is the guy that we do not like. Okay, all right, let's move on to part B. Now, this is the part that you were supposed to self-study, because I know you guys all do the readings, right? But we're going to take a look at CX in this structure, and we want to look at the hybridization around the atom. Now, if you guys didn't read about hybridization yet, I'll just give you a brief primer. But for hybridization groups or hybridization, we want to look at the charge groups around the atom. Okay, charge groups. Now, basically, what kind of connections or lone pairs it has. Now, if you guys take a look at this CX, how many bonds does it have? Not sticks, but number of different bonds. Yeah, 3. There's one charge group here, which is a double bond. We have one charge group here, which is a single bond, and another charge group here. So there are 3 charge groups on that carbon, which means that it's going to have a hybridization of sp2. Okay, now if you have no idea what that means, go do your reading. Okay, but 3 charge groups. So S, you can kind of think of it like this, SPP, but we don't want to say PP because it makes people laugh, so we do SP2. Or makes me laugh because I'm 12. All right, if we go to part 2, how many single and pi or sigma and pi bonds does it have? Now, sigma bonds or single bonds are going to have 1 sigma bond. Okay, so single bonds, they equal 1 sigma. Okay, that's the Greek thing for sigma. Okay, maybe we'll get there with COVID. Okay, and then for pi bond, or sorry, for doubles, if you have a double bond, that's going to be 1 sigma and 1 pi bond. Okay, so if we look at this structure right here, it has 1 double bond and 2 single bonds. Okay, so how many total sigma bonds is that? Fingers? 3, because each single contributes one sigma bond, right? 1, 2. Double bond has 1, so that's 3 sigmas, and the double bond contributes 1 pi bond. And if you guys have no idea what I'm talking about right now, go do your reading, go watch some YouTube videos, because this was part of the self-study portion. Okay, so that's going to be the answer for part 2. Part 2, there are 3 sigmas and 1 pi. All righty, ready for the last part? And then we're all done with this torturous day. Okay, the last one is you're going to have to draw a new molecule, a Lewis structured molecule for C2H4O. It's saying a hydrogen ion attaches to the acetyl ion and it creates C2H4O. Draw the Lewis structure. So I'll give you guys 2 minutes to do that. We'll go over it and then we will finally be done. Okay, so draw the Lewis structure. You will have to know how to draw these Lewis structures for the AP test, so let's keep that in mind. Alrighty, let's start going over this. Now, we know that we want to start off by counting the valence electrons available to us. So we're gonna look at carbon. There's 2 carbons, that's gonna be 4 each, so 8 plus 4 from the hydrogens, and then 1 oxygen, which is 6, and that's gonna give us 18 valence electrons to work with. Okay, we know that carbon likes to be in the middle, so we're gonna put carbon towards the middle, and hydrogens tend to be on the outside. Excuse me. And oxygen tends to be on the outside as well. So we're going to put hydrogen here, hydrogen here, hydrogen here, oxygen here. So if we take a look at the structure we had for the acetyl ion, we knew that the correct structure was this one right here, right? This was the structure that we said was on the left. And we said that's the correct one, with oxygen having 6 valence electrons. So I'm just going to start off by copying down that structure. And then all we need to do is add the hydrogen ion, okay? So we're gonna add a hydrogen ion. Wait, hold up, I'm doing something wrong here. Oh, it's C2H3O minus, my bad. Actually, that should be fine, never mind. Okay, so we have hydrogen, sorry. So we're gonna add a hydrogen here. Now the question is, where do we attach the hydrogen, right? Because we can attach the hydrogen here to the carbon, we can attach it to this carbon, or we can attach it to the oxygen. And so what we want to do is we want to figure out what's going to reduce the formal or keep our formal charges happy. Now, I'm going to give you guys a hint. If you guys have something of structure like this, right, a carbon attached to a carbon and an oxygen by itself, if you ever add a hydrogen to that, hydrogen is usually going to want to attach to the oxygen. Okay, because that'll reduce the formal charges the most. So keep that in mind. If you have a lone oxygen, okay, with 6 valence electrons, usually that's the one hydrogen is going to want to attach to. Okay, usually. Okay. Now you would want to go through and check the formal charges. I'm not going to do that today just because we are running out of time. But theoretically, you could test putting it here, putting it there versus there, calculate the formal charges, and that's going to give you what you want. But just to let you guys know, for the sake of time, it's usually going to attach with the oxygen. It makes a group called an alcohol group, which is an OH bonded to a carbon. Okay. Alrighty, guys. Well, great job today. I know it's very long. We have our full-length exam next Wednesday, so just make sure you prep for that. That's also the last day to turn in any extra credit or any homework assignments you might be missing.